Hello students, I welcome you all in the next session of a Strength of Material, Unit 3, Bending Stresses in Machine Elements. Myself, Professor M.V. Bhadak. Today I am going to discuss relationship between stress, strain and radius of curvature. Now your next slide represents two different figures. Now what this slide represents, simply supported beam with different end, different conditions. First figure represents no load condition, when the beam is supported at two ends and there is no load acting over the beam. That condition is called as a no load condition. And in the second figure, which represents the beam which is simply supported at two ends, and the point load or concentrated load is applied exactly at the center of the beam, which is represented by P. P is the load, concentrated load acting at the center of the beam, exactly half of the length of the beam, which is represented by L by 2. L is the total length of the beam. This is the two different conditions of beam, simply supported beam. We are using simply supported beam to identify the relation between stress, strain and radius of curvature. Now next slide represents neutral axis. What is a neutral axis? When the load is applied, in the previous slide there is a no load condition and load condition. When there is no load acting over the beam, beam remains constant. It is not deformed from its original position. But when the load is applied over the beam, then the beam may deform or deflect from its original position. So how it will deflect, it is mentioned in the next slide. So also in this slide, neutral axis is also mentioned, and it is represented by blue dotted line. What is a neutral axis? The axis which is passing through the center of the beam, which is represented by blue colored line, that is called as a neutral axis. Its length remains constant when the load is applied and no load condition. When the load is applied to the beam, then you can identify sagging position of a beam. We will observe in your second case of a neutral axis image here, and theta is the angle between angle AOB. O is the origin where the beam intersects. When the load is applied to the beam, then we can identify upper portion of a neutral axis may get compressed, then the compression stresses will induced above the neutral axis. Here from the neutral axis upper portion of a beam, you can identify compressive stresses are induced, and below the neutral axis, due to application of a load, tensile stresses will induced into the beam. From this line, neutral axis to this portion, tensile stresses will induced into the beam. Now we are considering the small section of a beam. When the load is applied to the beam, beam may get deformed, and we are considering the small portion of a beam to identify the relation between stress, strain and radius of the curvature. This is the next modified figure of relation between, or to derive the relation between stress, strain and radius of curvature. You can identify, or we can give the names to this point here. If it is A, this is B, C and D. When the AC intersect and CD intersect to origin O here, it makes an angle theta, and R is the radius for this dotted line. Dotted line represents your neutral axis. It is also mentioned here, this is the neutral axis. Then R is the radius of that neutral axis. When the load is applied to this beam, then beam may get deformed, and deformed beam is denoted by neutral axis at the center position, that is called as a radius. And this hash portion, red hash portion represents, this is the small portion we are considering to identify the relation between stress, strain and radius of the curvature, and the thickness of that small portion is denoted by small y. Now we will see the derivation of that stress, strain and radius of curvature. As we have seen in previous slide or previous image, length of the neutral axis, this length of this neutral axis is not equal to the AB. So we have to evaluate or identify the length of that length of that AB. So we can write this length of AB as a R, which is the radius of neutral axis, radius of that neutral axis, and theta. It is the product of R and theta, because when the load is applied to the member, it may get deformed, and we are considering this as a curved portion. So AB is equal to R theta. Now let us consider the very small layer thickness equals to the Y. As we have mentioned in previous slide, this small portion we have mentioned here with the help of the red color hash portion, and its thickness is small y. So we are considering that thickness, and we are identifying the relation. Length of bottom line of CD is also not equals to the length of the neutral axis. So we need to identify the length of that CD. So how much is the length of that CD? It is the addition of this R plus small y into the theta, which is mentioned in this slide. CD is equal to R plus y into theta. Now we have to identify relation between the stress, strain and radius of curvature. So what is strain? Strain is defined as the ratio of a change in length over the original length. Now here we have mentioned strain by using notation epsilon is equal to delta L by L. Now delta L is the change in length. Change in length is equal to CD minus AB, and original length is denoted by capital L is equal to AB. Now we have to calculate strain here. Strain epsilon is equal to change in length to the original length. So what is the change in length? Put the values of change in length to the original length into this formula, strain formula. So CD minus AB divided by AB. Now put the value of a CD and AB into this equation. So what is CD? CD is equal to R plus Y into the theta minus AB as a R into theta divided by R into theta. After rewriting this equation, we will get the final equation as a Y into theta divided by capital R into theta. Theta may get cancelled, and finally we will get this strain epsilon is equal to small y divided by R. Now we have to identify the relation between modulus of elasticity and radius of curvature. So modulus of elasticity is the ratio of stress to the strain along the same axis within its elastic limit. So this modulus of elasticity is denoted by letter capital E, and capital E is equal to stress divided by strain. Stress is denoted by sigma here, and strain is denoted by epsilon. So we know the value of a strain here, which is already